calibration of hypersonic tunnel. Okay, calibration term is applicable to any component when we purchase anything. Okay, in any lab, we can do calibration initially when we purchase anything before conducting any experiment. So I'd like to introduce or recall the meaning of calibration. The goal of calibration is to quantify and to improve the accuracy of an instrument or component used in industrial systems. Okay, we can quantify the results and can be compared with standard results. So we can do something to match our experimental reading with the standard results. The calibration of the test section of a hypersonic tunnel is generally the same as that of a supersonic tunnel. What we do in supersonic can be followed in hypersonic also. Okay, in supersonic we can check the pressure if manometer or other devices are used. Similarly, here also we can use the output verification with standard data. But in supersonic we can consider some samples, but here we can do calibration for the entire range of operating conditions. Okay, we can do calibration for the entire range of operating conditions of the hypersonic tunnel. So calibration means to predict the quality of the component and to quality of the component in terms of measured data with the standard data. The calibration what we followed in supersonic is same as hypersonic calibration methods. In supersonic we can do calibration for certain range of conditions, but here we need to do calibration for the entire operating conditions. Okay, we can face some technological issues in designing and constructing a hypervelocity or hypersonic wind tunnel. Supply of high temperatures and pressures for times long enough to perform measurement. Okay, we need to retain the same value of temperature and pressure and reproduction of equilibrium conditions. Okay, maintaining the same pressure for same Mach number in the hypersonic regime is a challenging one, and we can see some damages in the tunnel because of overheating, and we can act wisely to capture all the reading and the power requirements for the hypersonic tunnel. Okay, all adds the complications to hypersonic operations. Supply of high temperatures and pressures for long times, and reproduction of equilibrium conditions, and structural damage because of overheating and the fast instrumentation, power requirements, they all made big challenges in hypersonic tunnel operations. Okay, we can see some components: high pressure airline, drying unit, pressure tank. Okay, uh, it is at 16 bar pressure, and the pressure control valve, quick acting firing valve, insulating barrier, heater coil, welding generator, setting chamber, contoured axisymmetric nozzle, diffuser, enclosed jet section, vacuum tank, motorized slide valve, vacuum pump. Okay, now we discussed how to do calibration. I told some points on hypersonic tunnel calibration. Okay, next we can see some more effects while calibrating the tunnel. Yeah, we need to know these effects, then only we can predict the readings. Nozzle wall boundary layers are much thicker and subject to large changes in thickness due to operating pressure and temperature than in supersonic tunnels. The nozzle wall boundary layers are much thicker than the nozzle wall boundary layers in supersonic case and subject to larger changes in thickness due to operating pressure and temperature than in supersonic tunnels. So, the larger changes in thickness is due to operating pressure and temperature values. Here we can keep higher values of pressure and temperature. That's why okay we can use thicker, much thicker boundary layers. Also, the real gas effects make test section Mach number quite sensitive to total temperature. So gas effects make test section Mach number quite sensitive to total temperature. Next, the area ratio required for Mach 7 increases about 24% as the operating temperature increases from 1000 degree Rankine to 3000 degree Rankine. The area ratio required for Mach 7 increases about 24% as the operating temperature increases from 1000 to 3000 degree Rankine. The area ratio to attain Mach 7 increases about 24% as the operating temperature increases. So we can note the so area ratio, operating temperature. Okay, we can know the relation. If you want to keep Mach 7, you can see the temperature rises from 1000 to 3000 degree Rankine Fahrenheit. This rise is about 24% as operating temperature increases. So area ratio changes is about 24% as the operating temperature increases from 1000 to 3000 degree Rankine. Okay, next is caloric imperfection. Is a condition in which a gas specific heat capacity changes as opposed to being a constant value. This occurs when some of the flow's energy is used to excite the vibrational modes of diatomic molecules in the gas. So normally we can see constant specific heat, but in the hypersonic tunnel, calibration may result changes in specific heat capacity. This occurs because of the vibration of the diatomic molecules in the gas. Diatomic molecules means molecules composed of only two atoms of the same or different chemical elements. So our tunnel calibration needs to show this gas specific heat changes also. Also, a significant axial temperature gradient may exist in the settling chamber. Okay, we can see temperature gradient. Good value of temperature gradient in the settling chamber with the temperature decaying as the nozzle throat is approached. Okay, till the throat section, the notable axial temperature gradient may decay. So we can note these changes also. We need to note this change also while calibrating the hypersonic tunnel. This is the diagram measurements of the stagnation temperature along the axis of the settling chamber. Here solid circles are from measurements made in the test section, not the throat as plotted. So okay, we can see changes in the settling chamber, in the throat also. The circles, solid circles, indicate measurements made in the test section. Here the solid circles plotted at the nozzle throat station are from test section temperature measurements. Here we can see the perfect fit with the settling chamber temperature and the throat temperature. This indicates there is no temperature loss between throat and the test section. So if both the temperatures are in the same place, we can ensure no temperature loss between throat and the test section. Instead of trying to eliminate the axial gradient, the practical solution is to measure settling chamber temperature as near the throat as possible and to determine what the losses are between the measuring station and the throat so that they can be applied to the calibration and test data. So the axial gradient may be there in settling chamber. This can be decayed in the nozzle throat. So the perfect fit of temperatures in the graph indicates no temperature loss between throat and test section. So the axial gradients are important. This can cause some serious changes in the flow characteristics in the hypersonic tunnel. In addition to axial gradients, serious lateral temperature gradients in the settling chamber are the rule rather than the exception. We can see temperature gradients in lateral direction also in the settling chamber. They should be eliminated before uniform flow can be achieved in the test section. We can prefer uniform flow in the test section in any tunnel. So we can avoid this lateral temperature gradients along with axial gradients. So in order to avoid axial gradient, we will measure settling chamber temperature as near the throat as possible. Settling chamber measure, and we can measure throat pressure also. This is the last slide, then we can wind up. When a conical nozzle is being calibrated, it is necessary to make detailed surveys of the portion of the tunnel in which models will be tested. Okay, we can look at the portion where we will keep the model. And the flow gradients will exist, and the local Mach number and the gradients must be known to reduce and evaluate the data properly. I told about axial gradients, lateral gradients, and the flow gradients, changes in Mach number. So these changes, okay, we can attain the expected Mach number without reducing or increasing the target value. So the adjustment or calibrations can be done to avoid those gradients and meet the required operating conditions.